Now, I know some of you are thinking, oh, acid-base titrations, this stuff was easy back in school, because whenever we titrated stuff, we always titrated things like sodium hydroxide with hydrochloric acid. And that's all nice and good, but you have to remember that not all acids are going to be hydrochloric acid, and not all bases are going to be sodium hydroxide. Okay? Sometimes you have weak acids, weak bases, and you can't use the calculations that's used in high schools to figure out how things work in the real world. Okay? So let's review a little bit of what an acid-base titration is. Okay? General overall reaction of an acid-base titration is I've got some sort of acid, and it's represented as an acid because it usually leads the molecular formula with an H. And that is going to react with some sort of base. Okay? And when these two things react in the presence of water generally, okay, what we are going to end up with is A minus plus HB. And that's going to be plus. And all of these things are going to be in solution. Okay, so I'm not going to write aqueous here just to represent that. So that's the generalized reaction. Okay? Now, whenever we titrate something, we generally want to get to what's called the equivalence point. And the equivalence point is the point at which the concentration of HA is going to be equal to the concentration of B. All right? That's when we have equivalence. Now, if you think about equivalence, and the concentration of these things is so low at that point, and it's going to be hard to try to guess or identify when we actually get to the equivalence point. I mean, we're talking 1 times 10 to the minus 7 atoms, or as far as not atoms, but concentration values go. So, having a few extra atoms on one side or the other is going to bias us, especially when we're working with strong acids and strong bases. Okay, so oftentimes I don't get to the equivalence point. I don't think I've ever, as a chemist, gotten to the equivalence point. But what I have gotten to is something called the end point. And the end point is the point at which we stop titrating. Okay, so once we see a change, this is generally when we see that pink color persist of phenolphthalein whenever we're adding this to a base. Okay, or whenever we're adding base to acid. So once you see that color persist, that's what we call an endpoint, and this is where we stop titrating. I did mention that there's something called phenolphthalein, and this phenolphthalein is what we call an indicator. And an indicator is something that we use in the solution to identify when we have a transition from one pH range to another pH range. Okay? So this identifies pH range changes. Okay? Now, there's a couple more definitions. There's strong acids and bases, and this is just like electrolytes. Okay? And weak acids and bases. And when we use these two terms, strong means that it completely dissociates in the solution. And weak means that it does not completely dissociate. To give you an example of these two types of systems, right? Strong acids, like hydrochloric acid, dissolve completely when they hit water. When they dissolve completely when they hit water, that means all HCl is going into H3O plus and Cl minus. That's why those acids are very strong. Same with sulfuric acid. Same with the nitric acid, okay, or hydroiodic acid, something like that. All of those are very powerful acids. When we get down to weak acids, it doesn't mean that they're not good acids. Acetic acid or vinegar, whenever we taste that because it is a weak acid. It's dissociating to a small amount enough of a point that our tongues can pick it up and identify it as vinegar. Okay? Same with weak bases. Whenever you pop a soda can, okay, that's carbonic acid that you're seeing there. Carbonic acid is a weak acid. Okay? That's because carbonate is dissolving inside of it to generate the acid. When we get to weak bases, this is why, sorry, I kind of got confused a little bit there. But when we get to weak bases, we're talking about something like sodium carbonate, okay, or sodium bicarbonate, which is baking soda. It's a weak base. Okay, strong base would be something like sodium hydroxide. That sodium means it's going to completely dissociate. Sodium bicarbonate, because it's got an H on it, generally not considered a very strong base. Okay. All right. So these are some identifying features of different acids and bases. All right. So here's a classic acid-base interaction: hydrochloric acid with sodium hydroxide. Right. Strong base, strong acid. Now, when these two things interact, what I'm going to get out is H2O and sodium chloride. All right? So this is the textbook definition of a neutralization. We've lost all acid, we've lost all base, so everything's become neutral. Okay? Now I know what you're thinking, Dr. Roy, what does this look like on a graph? Because we got to graph it, right? Everybody's thinking that, right? Okay, good. So I'm going to graph this, and what I'm going to do is I'm going to graph it like a titration. Okay, and I'm going to identify this over here as our pH scale. And I'm going to start down here with 1. Okay, so it's an acidic scale. Go over here to 7, and up here I'm going to list 14. Down at the bottom, I'm going to list the amount of NaOH that we've added. Okay? Now, in order to define this, what I'm going to do is I'm going to identify certain starting values. Okay? So I'm going to start here with 25.0 milliliters of 0.1 molar hydrochloric acid. And what I'm going to use here is 0.1 molar sodium hydroxide. And we'll be monitoring the pH as we're adding NaOH to it. Okay? So if I come over here and I add, say, 10 milliliters of NaOH to this solution, what am I going to have at that point? So at this point, on my scale, I am going to have a pH which is about right here. And why is that the case? Because I've only added 10 milliliters of sodium hydroxide, which means I'm going to have at this point 15 milliliters of HCl remaining. Okay? Over here, when I've added 0, I had 25 milliliters remaining. Okay? What if I add 20 here? Right? When I get to 20, I see a very slight kind of uptick there in my pH, okay, but it's still lingering right there in the 1 scale. I'm just becoming a little bit more dilute. So my scale hasn't really changed that much. I've still got a strong acid present in my solution, but I have less of it. At this point, I've got 5 milliliters of HCl. Okay? Now, when I get to the equivalence point, if I am a master of titration values and I add exactly 25 milliliters of NaOH, I'm going to reach something that's right in the middle. And that point that's right in the middle is going to be my equivalence point. Okay? This is at pH 7. So right here, this is my equivalence point. Okay? But once I get to 25.1, or say, let me just do 26 here, 26 milliliters, my pH has now jumped way up here into the basic level, right? Where I'm up near 14. At this point, I'm becoming very, very basic because now at this point I'm adding a lot of base. And when I come over here to 30, I've got 5 extra milliliters of base, so my pH is way up here. Okay? So what ends up happening is when I graph this thing, it looks like this. All right? So at this point, I transition from acid into base. Okay? And that's what my curves are going to end up looking like. All right? There's a giant slope there, and it's kind of hard to control how much material I've added at that point to really get to the equivalence point. And generally, whenever I'm doing a titration and I see that color change shift, okay, and I see that pink color of phenolphthalein, it's generally going to be right about here. Okay? And at this point, that's what we call the end point. Generally, they look at that and we say, and that for strong acid, strong base titration, that's good enough. At that point, I've reached a point where I've just gone barely past the equivalence point to get my endpoint. Let's call it there, and I'm going to say that that's as close as I can get to this value. I can do something called back titration with a little bit of acid to see if I went over too much. Okay, so that's something that's also possible. Okay, depends on how far over you are. Okay, so what we're really looking for in any titrations is not really the equivalence point, but we are looking for the endpoint. All right, so I've got two questions here that deal with acid-base titration. All right, and the question here is how much 0.5 molar HCl is needed to neutralize 10 milliliters of 0.25 molar NaOH and 10 milliliters of 0.3 molar calcium hydroxide. All right, let's do the top one first. That's relatively simple. Okay, and what I have at this point is I've got 0.5 molar solution of HCl and a 0.2 molar solution of NaOH. At this point, I should find out the number of moles of each. Okay, so the number of moles that I've got here with sodium hydroxide, that's equal to big M is equal to moles over liters, right? Yeah? Okay, so that's not too hard. All I have to do is take 0.25 and divide it by 0.01. 0.250 divided by 0.0100 liters. Okay? Wait, I've done that wrong. Why didn't you tell me I did that wrong? Okay? Sorry. I have to rearrange this. Big M times L is equal to moles. Okay? Right? All right, so now at this point, do it correctly, and we'll get a different answer. 0.250 molarity times 0.0100 liters. And at this point, what this is going to give us is number of moles of NaOH. Okay, now I can do this math in my head. Okay, so I move 2 decimals over, I'll move 2 decimals over this direction. So what I get is 0.00250 moles of NaOH. Okay, now at this point, because I've got that number of moles of NaOH, I know that's going to be the same amount of HCl that's going to neutralize it. Okay, how do I know this? Because OH has a -1 charge, and HCl, the H plus, has a +1 charge. So it's got to be a 1-to-1 ratio. Okay? That's the number of moles of NaOH. Now all I have to do is figure out the number of liters that I got here. So for HCl, big M is equal to moles over liters. Since I've got moles there and I've got molarity, rearrange the equation. So now I've got liters is equal to moles over molarity. All right, so 0.00250 moles. And this is HCl at this point. Notice those are the same. Okay, and I divide this by 0.500 molar. Okay, this is also, because big M is equal to moles over liters, moles over liters. So the moles will cancel out and the liters jumps to the top. Okay, so we do some math associated with that. Anything divided by 1/2 is going to be multiplied by 2. So I get 0.00500 liters of HCl, or 5.00 milliliters of the HCl, the 0.5 molar HCl. All right, does that make sense? Okay, we always want to go back and check these problems to make sure we haven't done something stupid like something I almost did over here, right? Okay, so does this make sense? This thing is twice as concentrated as the NaOH. So should it take half as much to neutralize the solution? Yes. Is this half as much to neutralize the solution? Yes. Okay. Good. Now, let's do this one down here. But I want to caution you because the ratio here of HCl to calcium hydroxide is 1 to 2. All right, so I'm going to need 2 HCl's to neutralize 1 calcium hydroxide. Go ahead and try that, and then we'll show you the solution and see if you're right. Okay, so hopefully you got the solution using it this way, all right? In this case, we did the same thing. Okay, big M times liters is equal to moles, right? And so we should have 0.00300 moles, of calcium hydroxide, right? All right, now down here, I've got 0.033 moles of HCl over 0.5 molar HCl. And what I've got now is 0.006 liters or 6 milliliters of HCl. Now, is this the right answer? There's something I caution you about this before solving this problem. Okay, this would be fine if this was monobasic, if it only had one hydroxide on it. But it doesn't, right? I need twice as much HCl to neutralize it because I've got two OHs there. Okay, so what am I going to do? Okay, I've heard some of you talking to your screen, and you're saying multiply it by 2, right? Because it takes twice as much HCl. So don't forget to do this. Multiply that by 2, and we get 12.0 milliliters of HCl in this case. Okay, that's the true answer. All right, do you see how we solved that? Go ahead and work the problems that have been assigned in this chapter, and get yourself nice and used to doing this, because we do this all the time in chemistry. We do this in Chem 2, we do this in analytical chemistry, we do this in instrumental analysis, we do this in PChem. Everywhere except organic lab, you can run into this stuff. And even sometimes in organic lab, it might happen. So make sure that you are well solid and have this as a fundamental to your chemistry repertoire.